listens to this. Okay, well, the light's coming on. As I was telling Bill earlier, tomorrow is the 60% completion date for Title IV funds. That's what's on the administrative calendar. Now, what that means, my understanding of it is, if I think Title IV funds or any of your Pell Grant, those kinds of things, if you are on some federal funds like that, and you withdraw from a class in a full term before the or any term before the 60% completion date, you technically owe them the money back. If you remain in the class through the 60% completion date, then you don't owe the money back. So that's what that gets to be. So anyway, tomorrow is the deadline for that. So after that, if you know of anyone who feels like they're going to be in danger of failing or making a D, that would be better to wait until after tomorrow to withdraw from the courts if they're on federal financial aid. And then today, the volleyball team is hosting Bevel State Community College over on the Birmingham West Campus, the Arthur Shores Fine Arts Building, which is also the gymnasium, and that match is at 6 p.m. And if any of you can make it, we've got a really, really good volleyball team. I think it would be pretty exciting to watch. I'll be here until after 6, so I doubt if I'll get to catch it. So, anyway, let's go on and get set up from the current slide. And any questions on anything we've done so far? I'll return your papers to you. Is there any question on that either? Okay. I tried to mark where I thought I may have seen where at least an error occurred. I don't know if it was the deadly error or not, but I tried to locate those. Now, they go into this, and it is sort of important. They're not used that much, but they do throw them in every now and then. And this is a little blurb on differential operators, okay? And just to give an idea, okay? You've all been dealing with plus signs. In a sense, that's an operator. It tells you to add what's on the front end of it to what's on the back end of it, okay? That, in a sense, is an operator. Not quite like they're talking about here, but it's just a symbol that tells you what's going on, okay? More specifically, d by dx is an operator, okay? That tells you take the derivative of whatever follows that, whether that's a f or y, whatever, you know. That's an operator telling you take the derivative of this, okay? You know, something with a superscript 2 means square it, okay? That, in a sense, is an operator. Now, this one's a little trickier. Something with a prime, that's, of course, a derivative 2, just like this one is. Something like this to the minus 1, this is the tricky one. It depends on what this is. Is this a number or a variable? That means inverted. You know, that means reciprocated. If this is a function, that means take the inverse of it, which is a different process altogether. So some operators are used for a variety of things in different ways. Okay? Those are all samples of operators. Well, here's another operator. Okay? Let's go back to this one. D by dx, or d by d something. Okay? Another way to express that is a capital D. Just a capital D. That means take a derivative. Okay? Now, if this is dy by dx, then we would write capital dy. Okay? That's the differential operator written as one letter rather than three, okay, with a bar in between. It's just another way to write that operator. But not only that, let's just do a few with it. What would this mean? D of cosine 4y. What would that be? What's that? Okay, well, without this, yeah, the independent variable is the variable you see.
The independent is the variable which you see.
Right. You're taking derivative of this dependent variable, which is only expressed as cosine 4y. That could be z, it could be stickman, it could be whatever it is, but the independent variable is y. Minus 4 sine 4y. Perfect. Exact. Okay? What would this be? D of 5x cubed minus 6x squared. (15x squared) minus 12x. Perfect. Okay? Now, they make this statement, which may feel natural to you, but I don't know if it feels all that natural. Higher order derivatives can be expressed in terms of d as in a natural manner. Okay? So if they're saying d by dx of dy dx, okay, that could be expressed a couple ways. Here's one. D by dx of d by dx of y. Right? Or d2y dx squared. All of these can be expressed as, guess what? D squared. You got it. D squared y. Okay, that's exactly right. D squared y. So higher order derivatives are powers of d. They look like powers of d. That's not really a power, but it's sort of like you're squaring. This is a d, that's a d. It looks like a d squared. So that's exactly what we do. So the nth derivative of y with respect to, I'm sorry, I can't read. That's the nth. Doesn't matter. Okay. The nth derivative of y with respect to x to the nth, what would that be in terms of the d notation? The capital D notation. To the n of y. Perfect, perfect, perfect. Okay. Now, if that doesn't get weird enough, then you can do other things like this. D plus 3. Now, they don't say of anything, so I'm just going back to our favorite old y. What would that be? Another way to write that. D y dx, let's just say x is our variable here, plus 3y. You got it. That's exactly what it means. Okay? How about this one? D squared plus 3d minus 4. And if that was all of y or any other variable, it doesn't matter. That would be d 2y dx squared (3 dy dx) minus 4y. Right. Okay. Now, what gets a little bizarre about this that could be written as d plus 4 times d minus 1 of y. Okay? Yeah, but that's stretching it, isn't it? Okay? How about this one? 5x cubed d cubed. Let me start over. Let me just start with a clean slate here, because I'm getting 5x cubed d cubed minus 6x squared d squared plus 4xd plus 9. Okay? That's also a differentiable operator. Whatever you have here, put some other variable other than x. X obviously is your independent variable here. So put y, z, m, p, q, stickman, whatever you want to do. I like y, that's perfectly fine. So you can have any variable, any coefficient function of your independent variable in front of your operator for your derivative, differential operator. That's what it's called.
Last term inside the lesson, is it a 9 or what?
The last thing, okay, this is a y, that's a 9.
That's a 9.
Doesn't make a lot of sense to have a y on both the in and outside. That would have to be something other than y in one of the two places. Okay. Now, in general, we can define an nth order differential operator or polynomial operator to be, I don't like this notation either, L. Now they're doing another operator. The L operator is equal to a sub n of x, just like we had. This is 5x squared, that's 5x cubed or minus 6x squared or 4x, whatever. D to the nth plus a sub n minus 1 of x, d to the n minus 1, plus dot dot dot, plus a sub 1 of x, d. I don't need a parenthesis there. I need the parentheses around my x. Okay, that's a sub 1 of x d plus a sub 0 of x. Okay, that would be another polynomial operator of your D operator. Okay? Now, what I don't like about it is quite often they use L as a linear operator. And just about every other course and everything else, this is not linear. Not in D. This is to the nth power. But they still are calling it L. It's just defining another operator in terms of this operator. Now, that doesn't make any sense if n is any number other than a positive integer. If n is fraction, decimal stuff, that doesn't work. In fact, you can't take a derivative, a fractional derivative. You can't do it. So the n does act, the superscript n is just like the polynomial, and that's why they call it a polynomial operator, because you can't have fractional forms or decimal forms or negative forms, because you're only taking whole number of derivatives. Okay, not a good way to phrase it, but I can't think of any other. Now, as a consequence of the two basic properties of differentiation, these are called the linear properties. So there again, we're using the term linear. D of C of f of x, that's supposed to be an f, okay, is equal to, you can, if this is a constant, pull it on the outside of d of f of x. Okay? That's the constant multiplier, where c is any constant. Now that can be positive, negative, fraction, decimal, rational, irrational, any real number. Any real number. In fact, I'm wondering if it might even be able to be complex numbers, but we're not doing too many things with that. Okay? Here's another, d of f of x plus g of x. This is the other part of the linearization, linear properties of this. That's d of f of x plus d of g of x. So that just goes back to the derivative of the sum is the sum of the derivatives, which we had way back, Cal 1. That was left over from that. Now, they get these all interwoven here. So the differential operator L, like we have above there, possesses a linearity property, okay? That is, L operating on a linear combination of two differentiable functions is the same as the linear combinations of L operating on the individual functions. Basically, just like we here did with D, same thing holds with L, but now compounded, you might say. So this linear operator is operating on some alpha f of x plus some beta g of x, okay? This would be alpha operating on L of f of x plus beta beta L operating on g of x. Okay, I think I got it right. All right. Now, for some reason, I don't know, my screen seems to be blinking in and out, which is not usually a good sign, but hopefully it'll hang with me for the rest of the day. So basically this is saying this linear operator, which is not linear up here, but it has these linear properties down here. This combines these two properties. Constants comes out, and sum of the two operators equal operators of the sum. This combines both of these with the next level up. And frankly, it's almost like they're getting carried away with the operators of operators of operators. But they do this, okay? Are you going to need to know this? I don't know. You might run into a few places where you need it. But here your alpha and beta are constants, positive, negative, fraction, decimal, rational, or irrational. And because of this equation, we say the nth order differential operator L, remember that's what this is, nth order differential operator L is a linear operator. It doesn't look linear up here, but it has the linear properties down here that's combined. Okay. Now, with that in mind, remember this chapter is higher order differential equations, so this L can be any order operator, okay? And maybe this is all this was getting at, okay? So I'm going to clear this off the screen so we can write anew this. Any linear differential equation can be expressed in terms of the D notation, because this is a linear operation type notation. For example, the differential equation y double prime plus 5y prime plus 6y is equal to 5x minus 3. write that in D notation. What would that be? D2 plus 5D 6y is equal to some, and yeah, you can just write that as 5x plus minus 3. I thought they were going to call it g of x. They usually do, but that's fine. I don't have to call it that. Okay. Or, actually, I did the second part, they did the first part. That could have also been written as D2 plus 5D. Well, this is the same thing. Okay, I'm sorry. It could have been written, perhaps firstly, as D2y plus 5dy plus 6y is equal to 5x minus 3. And then that could be written as the polynomial operator, and that could have been called your L. Okay? Now, L, because this thing right here can be, that's a, what do they call it? Nth order differential operator L. That's the second order differential operator L. That could be L of y is equal to 5x minus 3. Now, this could be called g of x, and that would be a non-homogeneous or homogeneous linear operator, differential linear operator in x. And then the homogeneous related term to that would just be equals 0. So you could then talk about L of y is equal to 0. That means you count the g of x as if it's equal to 0. Okay. All right. They talk about that just very briefly. Then they go to what almost seems like a brand new subtopic, and that's superposition principle. We've kind of been using this all along, maybe without realizing it, okay? Without maybe calling it by name. So here's what we got. Theorem, the sum or the superposition of two or more solutions of a homogeneous linear differential equation is also a solution. Okay, so here's what we got. Let y1, y2, y3, dot, 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 up to y sub k, I've got to keep up with this, y sub k, all be solutions to homogeneous nth order differential equation on some interval I. If that's the case, if all those are solutions, then this is guaranteed to be a solution. Y is equal to C1, C1 Y1 of X plus C2 Y2 of X plus C3 Y3 of X plus dot 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 plus C sub k Y sub k of X. That is also going to be a solution. Okay. where the CI's so many subscripts here, where I is going from 1, 2, 3, ... up to K, because there were K solutions, K constants, okay, or arbitrary constants. Okay, now basically what that's meaning is they can be any numbers in the world. There's no, it's not just for certain C1s or certain C3s or certain CKs. Any C you put in there will also be. So you have an infinite number of solutions. You have K here, but then you can combine these together and then just change and put in any constants in there. Real numbers, not whole numbers, real numbers. Any real numbers in there, you still got a solution. Okay? If those y's are solutions, then any linear combination is also a solution on that same interval. Okay. Now they start with k equal 2, they little proof, and then basically say you can carry it on from there. Now here's a corollary to that theorem. That's theorem 4.1.2. Here's a corollary to it. A constant multiple C sub 1 y is equal to C1 y1 of x is a solution of y1 of a homogeneous linear differential equation. Boy, this verbiage here is really stupid sounding. A constant multiple y is equal to C1 y1 of x of a solution y1 of x of a homogeneous linear differential equation is also a solution. So basically, if you just have one y, okay, and drop all the rest of those, then this, if that's a solution to your homogeneous nth order differential equation, then y is equal to C1 y1 is also a solution. So why write it? I mean, it's all covered in here, okay? But a constant multiple, and this is just saying that's your linearity principle. A constant multiple is also a solution, okay? And this is of a homogeneous linear differential equation is also a solution. Okay, so if the first one is multiply any real number by it, it's also a solution. That's a pretty straightforward corollary. Second one, a homogeneous linear differential equation always possesses the trivial solution. We already had that, I think. A homogeneous linear differential equation always possesses a trivial solution. That's an S there, not a D. I did it again, possesses the trivial solution. Y is equal to 0. All right. And if that, then any k times that, or c times that, well, any c times 0 is still 0. So that's a very trivial application of the previous one. All right, so let's do example 4. I think we can. The functions y1 is equal to x squared and y2 is equal to x squared log x are both solutions of the homogeneous I don't like writing all that out. Linear equation. And this is a differential equation, by the way. X cubed y triple prime minus 2xy prime plus 4y plus 4y is equal to 0. Number one, that's a homogeneous solution. On the interval 0 to infinity. Now, I put an open parentheses there in front of the 0. Does that need to be open? Or could I have a bracket there? Wait. Yeah.
Oh, I didn't even notice that on my page.
Yeah. Because of this log x here, 0 cannot be included. Log x is undefined. Okay? If the log x had been there, you probably could have gone minus infinity to infinity, but these would have been identical. But with the log x in here, no, you have to have that open parentheses there, because 0 is not on this, cannot be in the interval. But any positive number can be. So that's the biggest domain you can have for this, and it works. Okay? Now, by this, it says both of these are solutions to the homogeneous linear differential equation, this. Then, y is equal to c1 x squared plus c2 x squared log x is also a solution. On okay, on that same interval I, 0 to infinity. Now, trying to see if there's anything else you needed to do here. There really isn't. Okay? The function, here's another, that's all that one. Yeah, that's all there on that same interval. Okay? Here's another. The function y is equal to e to the 7x is a solution of y double prime minus 9y prime plus 14y equals 0. Okay. Now, we haven't been verifying these. Every time I stop and think, do we need to? It sort of gets to be a pain in the neck, but it's really not too bad to. But they've quit asking us to verify, so we're just going to take their words for them now. If you want to test those out at home, you can do that. I think you'll find it's true.
If it was on a test, I'd try and verify it.
What's that?
If it was on a test, I'd verify it.
Right. This one up here, because of the that one's easy. That one you got, every time you take a derivative, you got a product rule. Okay. But it's still pretty easy because one side of the product is going to be 1 over x, and that'll wipe out one of the x's that's on the other side. So it'll actually come out easier than you might think. This one's really easy to do, but let's not verify it. Well, just quickly. The second derivative would be 49 e to the 7x minus 63 e to the 7x plus 14 e to the 7x. So, yeah. So it does work. So it's not hard to do some of these. Others, it's a little harder. Okay. Now, so we're just saying that is a solution. Because the differential equation is linear and homogeneous, the constant multiple y is equal to c e to the 7x is also a solution. Okay. All right. The next statement, I mean, it's true. I don't see what their point is, but you can say y is equal to 9e to the 7x. That's a solution. Y is equal to 0 is a solution, right? C could be 0. Y is equal to the square root of 5. E to the 7x would be a solution. It doesn't matter what you put there, positive and negative 7 square root of 5. This is e to the 7x. They're all solutions of that linear equation. All right. Now, where this kind of feels like it's leading to, it may be leaning that way too, is sort of a discussion or an introduction to, I guess, linear dependence and linear independence. Okay? And these are basic to the study of linear differential equations. Notice you got lots of linears in here. Here's the definition. A set of functions f, goodness gracious, f sub 1 of x, f sub 2 of x, f sub 3 of x, dot, 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 up to and including. They use different subscripts for different reasons that I haven't figured them out why. I don't think it really matters at all. F sub n of x is said to be linearly dependent Okay, linearly dependent, okay, don't get the terms crossed up, on an interval I, if there exists if there exists constants C1 through Cn C sub n, that's an N, it looks like an M, not all zero. Such that C sub 1 F sub 1 of x plus C sub 2 sorry, my throat is messing up on me and it's hurting to talk, but I'm trying to let it kind of settle down a little bit. Okay, such that C1 plus C2 F2 of x plus C3 F3 of x plus dot 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 plus C sub n is what we were using, F sub n of x, okay, is equal to 0. Okay. For every x in the interval, if the set of functions is not linearly dependent, then it's said to be linearly independent. That's rather bizarre seeming, but independent. Okay, now let's step back and see if we can figure out, let's go back, what they're talking about here. Okay, we have a set of functions, however many they are, n, okay? They're different functions, unique functions, okay? If you have this set of functions, f sub 1 of x, f sub 2 of x, f sub 3, all the way up to f sub n, you've got them there. They're linearly dependent on some interval I if there exists some set of constants, C1, C2, C3, C4, up to C sub n, not all 0, such that you can put together C1 of F1 of x plus C2 times F2 of x plus C3 times F3 of x plus dot 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 all the way up to C sub n times F sub n of x, and you can find some constants, not all zero. Now, certainly if all the constants were zero, they'd have to be zero. Have to be, okay? But if you can find some set of constants, not all zero, maybe all but one, okay? Certainly all but two, you know, that would, then, and that would be true for every x in the interval, okay? Not just some particular x here. Yeah, you can find that true right here for that x. No, for every x in the interval, okay? Then that's said to be linearly dependent. In other words, these functions aren't, they're not, I can't say it without using the word, they're not independent of each other. One of them depends on some of the others. And here's what you could do. Like I said, at least one of them, those c's couldn't be equal to zero. So if you pulled that one out and then did the sum of all the others, and they had to be equal to zero, then that would be linearly independent. They're not linearly dependent or linearly independent. But if that one creates a zero there for every x in there, that's some value of c, not zero, that makes every one of those f's of n's or f's of i's or wherever you are in there, then that's going to be linearly dependent. Okay. Now, this will make more sense a little bit later. Now, have either of you had linear algebra yet? Okay. That's, you probably had it years ago.
About 60 years ago.
Okay. It's not quite before I was born, but, you know, getting close. So you probably run into linear independence and dependence before, if that's the case. But other than that, it may be something fairly new to you. In other words, a set of functions is linearly independent on an interval I if the only constants can be zero. You cannot put together any combination of those and set it equal to zero unless every one of those is zero. Okay? That means they're linearly independent. So that's where I tend to start from that case and then say, and if one of those constants doesn't have to be zero, then it's linearly dependent. They start it from the dependent and then say, if that's not the case, it's linearly independent. For every x on the interval, all those c's have to be zero. That's linear independence. Okay. Now, here's a function. Alpha of x equal x. Okay? That's the identity function. Okay? Pretty simple one. You've had it from the beginning. That goes through the origin. It doesn't look like it, but it does. Okay? Now, here's another function. Give me another color. Pick a color, any color. Green? Okay, green. Okay? Here is our good old pal, the absolute value function. Right? The green one there. Absolute value of x is going to be x. Looks a little similar. Alpha, yuck. Okay. Now, are these two functions linearly independent or dependent of each other? Okay. Is there any way that you could combine these two together and for every x in the domain, you make it true? If you if you use this side, they're they're dependent. Obviously, they're the same function, okay? If you use just this side, you can say, I'm sorry, I shouldn't use both F's there. This should be F1. This would be F2, and this would be F1. Sorry, I forgot. It can't be the same function, okay? On this side, you can say F2 is equal to minus F1. And those are linearly dependent. These are dependent because they're the same function. These are dependent. But for every x on the domain, you can't say that this one says F1 is equal to F2. This says F1 is equal to minus F of x2, right? Or F of 2 is minus F of x1, whichever way you want to say it. But you cannot find a place that for every point on the domain, they're going to be. So those are linearly independent of each other on the interval minus infinity to infinity. From 0 to infinity, dependent. Okay, no question. Minus 0, infinity to 0, dependent. Well, on the whole interval, there is no two constants that you can say unless they're both equal to 0. That everywhere on the domain, you can get those two to be equal to 0. Now, to me, that's not the best of examples to do, but it certainly is one. Now, let's see if we can do an example that makes a little more sense. Okay. What time did we get started? I meant to look at that before we did. Was it about 20 after? Was that about right? Okay. So now we're going, so we got started 10 minutes early, so we'll go to 35, right?
Yes.
Okay. All right. Should go longer because y'all let me get away with something less. Okay. Yeah. All right. Let's do example 5. The set of functions f1 of x is equal to cosine squared x, f2 of x is equal to sine squared of x, f3 of x is equal to secant squared of x, and F4 is tangent squared of x. Okay. Now, what would you think that is, that set? Would they be linearly independent or linearly dependent?
First thought is independent.
It's what?
Independent.
Independent. Okay, and why would you think that? Because they seem like totally different functions?
Yeah, because cosine's opposite of sine.
Yeah. Not
Well,
quite in some senses, but I think I know what you're talking about. Yeah.
Sort of.
Yeah.
Well, the C's won't actually, but you, F1, F2, you have to have a minus C is equal to the plus C. Not plus C, I'm saying.
Yeah.
A minus C of one of the other function.
Right. Let's let me do a linear combination of these. Okay. F2 of x plus F1 of x plus F3 of x minus F4 of x. What is F1 plus F2? 1. And what is F3 minus F4? I may have it wrong.
1 minus Sine squared x is cosine, so it's 1.
I may have it wrong. Let's see. We know these two add to be 1, right? And we also know that secant squared x is equal to tangent squared x plus 1. Is that not right? Okay. So therefore, if we do, I said it wrong. That would come up being, no, yeah. I think if I said 4 and 3 here, that might work. Okay, I'm getting myself confused here. If you have, let me do it the way I did the first time. Okay, 3 and 4. Get out of the way. Okay. 3 and 4. Okay. Then this would be secant squared x minus tangent squared x minus 1. Well, secant squared x minus 1 is tangent squared x. Let me do it the other way. F4 minus F3. That would be tangent squared x minus tangent squared x minus 1. Yeah, that would be it, wouldn't it? So these go out, and you have plus 1 minus 1 equals 0. So there is a linear combination of those 4 functions that can give you 0 without all the coefficients being 0, dependent. Because you know these two add to 1, and these subtracted this way give you minus 1 plus 1 minus 1. And that will be true for every value because these are identities. Every value of x is worth on that. Not just a happenstance here or there, every value of x. Okay? So that would be linearly dependent. Okay? And it says, and oh, I forgot this part. On minus pi halves to pi halves. Now, that's kind of important because they're not defined in some places. Like secant and tangent are not defined at negative pi halves or pi halves. So you have to have an interval where everything is defined, and those are defined. And these relationships are true everywhere, including in that interval. So, yes. So, not this one up here. But this one. F4 minus F3. Okay. Okay. All right. C1, C2, C3, C4, when C1 and C2 and C4 are 1 and C3 is minus 1. Yeah. Where C1 and C equals C2 equal 1, C3 is minus 1, and C4 is plus 1. All right. All right. Now, here is another way, and this is how I was kind of leaning toward, another way to express this. A set of functions, of n functions, F1 of x, F2 of x, F3 of x, dot, 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 up to and including F sub n of x. Okay? Is linearly dependent, okay, on an interval I if at least one of the functions can be expressed as a linear combination of the others. Okay? Of the remaining functions. Okay? So what if we had F1 of x, F2 of x, and F3 of x were linearly independent? No, are linearly dependent. Okay? On I, of that some interval I, if at least one of those can be expressed as a linear combination of the other two. Let's say that F3 of x is equal to some C1 F1 of x plus C2 F2 of x. Okay. Now, it's kind of what we did before with this the sine, cosine, sine squared, cosine squared, tan squared, and secant squared. If you could express one of those, in fact, a combination of two of them, equal to the other. So sine squared plus cosine squared was 1. And tangent squared minus secant squared was 1. So you could say secant squared is equal to tangent squared plus sine squared plus cosine squared. Right, so sine squared plus cosine squared is 1. And tangent squared plus 1 is secant squared. So you could express secant squared as a linear combination of the other three. That makes them linearly dependent just as well. Okay? So both of these are saying the same thing. Okay? But it has to be for all x on I. All x's in I. The set of m functions is linearly independent. Independent on I, on that same interval I, if no function can be written as a linear combination of the others. Okay. If there's just no way you can do it, that's it. All right. So let's go to, how are we doing on time? We got time, a little bit, don't we? All right. Example 6. Here's a set of functions. f1 of x is equal to the square root of x. Plus 5, sorry. Square root of x plus 5. The square root sign ends with x, okay? f2 is equal to the square root of x plus 5x. Square root of x ends there. f3 is equal to x minus 1, and f4 is equal to x squared. Okay. Now, any of you want to hazard a guess on whether that's linearly independent or dependent?
Well, I know the title of the example, so.
Yeah, it is dependent.
It is dependent.
Can you think of why?
That's what I was looking at.
All right. Here's what I look
They
at.
make a C equal 0, so I feel like that's almost.
Second.
They make one of the C's equal 0.
Okay.
I don't.
Well, they do this one,
Yeah.
because none of these terms have an x squared in it.
Right.
So if that has an x squared, it's completely independent of these. So this has a square root and a constant. This has a square root and a linear. And this has a linear and a constant. So you've got some sort of a combination of them all there. Okay, so if you multiply this equation by 5, you're going to get 5x minus 5. Okay? And so 5 times this one has to be, well, minus 5 times this one has to be in there to eliminate that. Okay? And a minus in front of this one will then eliminate this too. And the minus 5 here, let's see. All right, let's think on that a minute. Okay, 5 times F3 will be 5x minus 5. Okay, you can add those two together. If you do a minus F1, that's going to be a minus square root of x minus 5. Okay, do I have all my signs right? I hope I do. Yeah, I think so. Let's try doing this one, minus F2. That would be minus root x minus 5x. And then do a 5F3 would be 5x minus 5. And then do F1 equals square root of x plus 5. Add those together, right? These go out, these go out, these go out. So F1 minus F2 plus 5F3 equals to 0. So there is a linear combination of, there is a set of C's not equal to 0 that makes that 0. Of course, you have to do C4 equals 0. because there's no way you can get rid of the x squared. So, but yeah, 1, 2, or 3 of those c's could be 0, but not. Yeah, some that are not 0, and that would certainly be it. The other way of expressing this then would be that let's see, F1 would be equal to F2 minus 5F3. So there's, this expresses a linear combination of those two. Or F2 is equal to F1 plus 5F3. Both of those would work. So yeah, there are ways to do it, and obviously that would add to 0 without all the coefficients being 0. Okay. L4 has to be 0. I mean, C4 has to be 0. Okay. No way around it. Okay, so what I just said was F2 is equal to F1 plus 5F3. All right. Is it time?
Yeah.
Okay.
We started 10 minutes early?
Did we? That's what I was trying to remember.
Yeah.
Okay. All right. Sorry we didn't get quite as far as maybe we could have, but we got through example 6. Next will be solutions of, and again, this is 4.1, which is covering the whole world of higher order differential equations. We'll stop at some point here and start doing some very specific things. But these are general definitions that will work for them all. And we're still in 4.1.2. We've still got to do 4.1.3, and then we'll be through with this one. So homework exercises here. I think I gave you last time any of the odds 1 or 3, if they're in the back of the book. I think they are. 5 or 7, if those are in the back of the book. 9, if it's in the back of the book. 11, if it's in the back of the book. And 13, if it's in the back of the book. Then 4.1.2, any of the odds 15 through 21. And stop there. We'll pick up the rest of those next time. Okay. And we'll hopefully finish 4.1.2 and get good progress done in 4.1.3. Okay. So, were we all day today in 4.1.2? Yeah, that's where we started. Didn't get too far today, but it was a lot of different elements there. And pretty important you get these concepts down, because we're going to be using them kind of over and over and over again.